Go
So,
ahead. Yeah.
yeah, I just wanted to uh, give the disclaimer that if anybody has any questions or comments, or feel free to interrupt at any time. So, my name's Kochanski. I'm a upcoming PhD student. I work with Young in the statistics department. So, um, yeah, this is work that I had done, or we are currently still doing. I've actually been on a little bit of a tour in terms of going to a couple of conferences, presenting this work, getting some feedback on it, and I'm excited to present this work to you guys. And um, it's my background is more in statistics. I know there's a little bit of a wide range of backgrounds here, mostly in astronomy, but just excited to get some feedback on this work. That being said, I'll start. So yeah, this work we titled it "Statistical Properties of Solar Flare Dependency," and yeah, let's actually go into what that actually means. So, you guys probably know more about solar flares than I do. Yeah, we know that solar flares are characterized by a large eruption of electromagnetic radiation from the sun, and they can cause a lot of issues for us here on Earth. Um, Radio blackouts, increased radiation, and then yeah, I saw in some really rare cases computer malfunctions. There's I think on the Toronto Stock Exchange, they had a computer that was it was like supposed to be uh, fail proof, that during a large geomagnetic storm actually ended up failing. So they said it was like a one in some trillion odds it was going to happen. So they like to say that it was because of the geomagnetic storm, but who knows on that. So that being said, yeah, the motivation behind this research is, so I mean, there's a large group of people that work on trying to produce solar flare predictions. Just being able to give accurate and relatively correct predictions about whether or not solar flares are going to be happening. So a lot of machine learning, this is where the statistics comes in. There's a lot of machine learning methods that people have been applying because these are pretty rare events, relatively rare events. They're difficult to predict. So yeah, there's a plethora of different types of models that people apply to this in terms of prediction. So a lot of the I guess going through the literature, a lot of people have just been applying these off the shelf type models where they are just producing binary classification, basically saying whether a flare, in some interval in the next 24 hours, is there a flare or is there not, right? And I mean, I know this, or Yin Yang, I mean, being a statistician, we know that these machine learning models are not oracles. Yes, they do very well, but that being said, they're not magic. They have their limitations, and a lot of these models are producing similar accuracy in terms of actually being able to predict solar flares. So yeah, while the physical traits of the flaring process are generally understood from like a physics perspective, we don't really know much about the distributions that govern the solar flare. So that's kind of the main motivation behind this. This image on the right, and if I'm just telling you guys stuff that you already know, please feel free to stop me. This is just a snapshot of an image of the sun with basically each active region. Each square is an active region of the sun. So we have this satellite that takes these images every 12 minutes, and then a computer algorithm basically determines these sunspots, and then we put a box around it. We give that box a number, which we name. We give the active region a number, and then we track the generation of that active region as it moves across the sun. So cool. So yeah, here's some snapshots of some different active regions. So the y-axis is, I mean, each dot on the plot basically represents one solar flare that we observe from a given active region. So on the y-axis, this is how they characterize solar flares. There's actually A, B, C, M, and X. With each subsequent increase, there's a 10 times increase in the intensity of the solar flare. So getting a more increasing, the intensity is going up, and they also get more and more rare from each class. So you could see just by visual inspection, you have active regions which they appear to have some temporal clustering. Active regions that are more sparse in terms of flaring. We also see even in flaring, in sparse flaring, we see just by visual inspection potentially some temporal clustering.
Noah, quick question.
Yeah.
So the starting point of these graphs is when the active region is first identified. Is that why
Correct.
there are blanks? It doesn't really start flaring on for some time. Sometimes in some
exactly.
cases.
Yep. So sorry.
And just to follow up on that, so are you limiting this to active regions that form on the disk as we're watching, or could they be rotating in?
Oh, just on the disk, correct.
Okay, so for instance, the 6015, the lower right one, it seems to start flaring early in its life cycle.
Correct.
Okay.
Yep. Yeah. So these dates don't match up. Actually, the scale doesn't match up either. But some active regions they last longer, or it's potential that we don't have any sunspots, and then the computer algorithm that does this actually puts a box around and finds a new active region on the disk. So yeah. So sorry, that was a good question.
Yeah, I want to quickly comment on that because Vinay is pointing out something about the data about the data collection. So we know that a lot of the B flares and A class flares are not really being recorded in our list, so we don't really have those as data points here. But the active region identification algorithm that was published a long time ago, I think it was in 2007. It was really based on some identification of a potential polarity inversion line, which is gonna lead to a flare eruption, and based on some strong magnetic activities. So that means when the active region becomes identified, there should be some flaring events, maybe very small ones coming in. So it's not like a total quiet time. It's just not strong flares yet. In that sense,
but mostly undetectable in ghosts.
Yeah, it's like an undetectable sense. So this might mean something for our analysis for the weaker flares, but currently we're not really considering that aspect. Yeah.
So, all right, this is actually what leads into our main research question for which this whole research is motivated, which is what is the actual dependency structure that solar flares exhibit when they come from a single active region? So yeah, this is kind of I feel like a lot of these models, machine learning models that people have been applying for prediction, they for example, they do some screwy things such as they might do a random train test split where they just look at some interval of the covariates, maybe could be 24 hours before, and then they basically give a binary classification saying whether or not a flare occurred in some interval after those 24 hours. If you do it that way, if you do a random train test split, you're actually losing the information about any previous flaring that active region actually had. So yeah, does everybody, we're good at this point, all right? So yeah, so maybe I'll just motivate this with a motivating example of how we actually go about testing the dependency structure. So this is active region 1275, and this is the same exact plot as we saw before. And so, just by visual inspection, it appears like there is some temporal clustering in this active region, right? if there wasn't, we'd expect at least a more uniform, just the solar flares to be more uniform across the entire, observed time that we the time we observed the active. So one hypothesis we can test for just this single active region is basically whether or not the flares that occur within 6 hours of each other are independent or dependent events, right? So we're going to treat each flare as, a discrete event, and basically, at an extremely high level, one way you could think about it is that we are looking at the flaring distribution compared to the conditional flaring distribution. And basically, if flares are independent events, the additional information that a flare just occurred should not affect the probability that you're going to see a flare in the next 6 hours. So if no matter what, if they are independent, the information, if I told you that a flare occurred in the previous 6 hours, should not affect the probability in the upcoming 6 hours.
Another quick question, Noah.
Yeah.
Why 6 hours? What is special about 6?
So this is just a motivating example. So I'm just trying to show you guys this is just for one hypothesis. Obviously, this is actually more of like a nested hypothesis where we're not just interested in 6 hours. We're interested in a generalize it to delta hours, where we, range the amount of time that we.
Okay.
This is just a motivating example, and I actually, yeah. So I'll get to that.
Right, sure.
So yeah, how do we actually go about, and I'm going to try to argue that an equivalent hypothesis test is really just looking at the set of random variables, which is the flaring in the next 6 hours and flaring in the previous 6 hours, right? So it's just an indicator of between these two random variables. So how do we actually go about testing this hypothesis for this active region? So this is the active region that we had before. To actually get samples of that, the pair of random variables, we're going to actually break up the active region into 6 hour intervals. That's what these dotted lines are. And basically within each interval, just identify whether a flare occurred or not. So if a flare did occur in the interval, we mark it as a green box. And if a flare did not occur, we are coloring it red. And basically, to go about getting the samples from that pair, we just basically move along this active region, taking pairs from the next 6 hour interval and the previous 6 hour interval and taking samples. So if I summarize, taking two, subsequent intervals, and we do that for the entire active region, we can just summarize that up in a table. And for this active region, we can, we just have this table to summarize. And we all have taken a introduction statistics course. You can just run a chi-squared test of independence. And for this given active region, we actually get a p-value of 0.1592, which says that we don't have enough evidence to reject the null. And actually, there's on the appearance, first appearance, it looks like there's that they are acting as independent of that. However, I'm going to say that maybe we should consider some different tests. So if we were to unsummarize this data, actually there's a couple things wrong with this using a chi-squared test. One, chi-squared, yeah.
You have 52 observations, right? Is that the number of pairs you considered walking through? Okay, yes. But it depends very much where you start then, right?
Yes, absolutely. So yeah, there's actually, so we just started right at the beginning of like the first observation of the active region. In sensitivity analysis, we can actually, move that just a little bit forward or back and look at how much that changes the results. So another issue is that actually these are
the table tests is independent of phase though, right? I mean, because you're looking at, for every pair, you're considering from when the flare occurred to when the next flare occurred. So where you start should not matter. I mean, those vertical stripes or don't have any.
It matters because you're counting. You're counting the red-blue pairs and red-red pairs and blue-red pairs and blue-blue.
Oh, you're not looking at the flare peak time or looking at how.
No, we're kind of coarsening the data into 6-hour intervals because the flare peak time can be any time. It's like a continuously recorded thing.
Well, but the peak is always the peak.
Everything. Yeah. We're discretizing everything to be like 6-hour intervals. And we're also discretizing the flare intensity into flare classes. So this entire problem is like a discrete problem.
Okay.
Yeah.
Yeah, so the chi-square test, you need independent samples, as well as the expected values of each cell to be at least 5. And actually that's what we actually broke about this. So what about if we consider some other tests? And that's why we used a U-statistic permutation test. So if I unsummarize this table, right, we would have a column of indicator variable, which is the flaring in the previous 6 hours, and a column in the next 6 hours. So under the null, we assume that these two variables are independent. So basically, I should be able to permute the first column of the data. And if I were to summarize the and re-summarize the table, put it back into a table, the table should be relatively the same exact table. And that's basically what this U-statistic permutation test does. So basically, this is how we go about producing a p-value for when we have sparse flaring. We permute the first column of the data. We compute this BN statistic, which is basically the chi-squared statistic, except we don't have a denominator. And you repeat this n times, and you just basically compare this observed for the original table, this value, compare this to the distribution of these B's. And for this, we actually get a very significant p-value. We get something below 5%. So basically, this test came about because we broke a lot of the rules of the chi-square test. When we have a lot of observations, it's less of an issue. But I just wanted, this is the other test that we use for the hypothesis testing. So. So yeah, if we look at, so this is what Vinay, I only considered 6 because that was actually, I was trying to show the discrepancy between using the chi-squared test and using the this other U-statistic. So this is actually, instead of just considering just 6 hours, we actually vary the results across many different time intervals. And I mean, this plot just shows you the discrepancy between the chi-squared test and the U-statistic test. On the y-axis, we have the actual observed p-value from the test. And on the x-axis, we have the interval considered. I mean, obviously from this, these are discrete events we're considering. So it does not need to be monotone in terms of the p-value.
I mean, it's this, so it looks like the longer the duration, the more dependence there is. Is that what this is saying, that the p-value goes down?
So actually, I think after, so in really, really short intervals, within hours, we get that we get that they are more independent, but in longer intervals, we see that they're dependent.
I mean, with the really short intervals, you're probably just overwhelmed by just most intervals not having anything. So it's all zeros, right?
Yeah.
But then for very long intervals, I mean, why would we expect there to be any
we need the 24 hours is not very long in the solar flares setting.
I have this, you'll see in the next, I think the next couple plots, the 24, I think this, I only did 24 hours. This is just a snippet. I mean, I consider some pretty large intervals in terms of, you'll see that.
Okay, all right, let's look at that.
Yeah, I think in terms of, there's like a time when you see the most dependency between the two distributions. But then once you reach a certain interval, like consider a certain interval, you see like there's no dependent, or sorry, yes, they are more like independent. So basically that was just an example just for a single active region for a single hypothesis. And I just wanted to show you that so that I can actually, when I talk about the results from each active region, it's clear about how we actually go about testing this hypothesis. So we used an entire catalog, which is basically an entire solar cycle, about 12,500 solar flares from over just over 1,000 active regions. These are all just basically from I use their daily solar events, which includes a lot of other information, but we just did solar. So I don't know if this would be a good question, if other solar events could potentially be dependent on solar flares or vice versa, or because I mean, we only did this analysis just looking at solar flares. I'm not sure. Again, my astronomy is not as rigorous as others.
So what other solar events are there? I mean, your solar astronomy may be better than you think, than to some of us. I mean,
yeah, do you remember what solar? I mean, I could look it up.
So what do you mean by solar events?
Yeah, they
about flares, CMEs, and NCPs.
Yes.
Yeah. So there's a solar flares, which we have a large number of them, and the stronger solar flares can potentially lead to something called coronal mass ejections or solar energetic particles, and those are the very strong and even sparser events that has a lot of impact on the Earth. So because of those issues, we are particularly interested in the solar flare events that are of class M and above, and the flare classes are classified based on a thresholding scheme. If the peak intensity exceeds a certain threshold, it's classified as M class or X class. So in this particular work, we're particularly interested in how can we characterize the flare dependency structure such that in the future, when we build our prediction models for solar flare events, we can properly account for the history of active region to make a personalized prediction of solar flare events for each active region as they emerge from the disk. So that's the purpose at the very beginning. And then with that purpose in mind, we're interested in testing out, does the weaker flares lead to more stronger flares? Does the stronger flares lead to more stronger flares in the future? Or does the weaker flares also lead to more weaker flares? So there's a bunch of hypothesis testing that will be done, and actually NOAA has been working on that to give us a thorough picture about the entire flare dependency structure so that we can take more informative steps for our modeling for solar flare predictions in the future.
Right. So that there's more to it than just worrying. I mean, you could imagine a situation where you wanted to mix other kinds of events like coronal mass ejections in here. But I guess they're much less common. But so you could try to predict coronal mass ejections from the flare history.
Yeah,
or
exactly.
That's just the tip of the iceberg, though. You could try to predict.
Yeah, exactly. This is the one
future flares from past flares. Yeah.
Yeah. This is a very small tip of the iceberg because we had a paper in Space Weather last year about predicting solar energetic particles or solar proton events based on strong solar flare intensity and fluxes. So that's why we're particularly interested in solar flare events. And Guan has a question that I think NOAA can answer, right? In the chat.
Oh, yeah. Yes. So yes, you're right. We are considering, we're not considering the X-ray class at the moment. these tests. We're considering all flares as equal. Yeah, we actually do consider the X-ray class, and I have some results to show you guys something.
Yeah, but that's a very good point, Gwen. So the thing is that we merge all the flares together for now, but then we also are interested in the class-specific dependency testing that I think Noah has already got some results. I'm not sure whether he's showing that today or not. But that's also another reason why we particularly are interested in the U statistics method instead of the chi-squared, because when you zoom into the stronger class, it's even sparser.
Yeah, and then we also consider two types of results. One, which we consider homogeneous and heterogeneous. The main difference in what I actually mean by those two phrases is when I say homogeneous, we're just pooling all the information from all the active regions. We're assuming that all of the active regions are produced with like distributions. And then the heterogeneous results are when we are considering each active region as its own. We're doing one hypothesis test on each active region. So the homogeneous, we're pooling all the information from all the active regions. Heterogeneous, we're basically looking at each active region as an individual. So here's for the homogeneous results, this is when we do not consider the X-ray class. And basically, this is when we are considering many different intervals. And this just shows you that we basically get significant results, except at around 4 days, which we see that the p-value actually becomes insignificant, meaning for this short interval, the flares appear to be independent as opposed to dependent. And I presented this last week at AAS, and just talking with some astrophysicists, I was like, yeah, I don't know if there is some physics equations or something that can explain this, but it also could be a artifact of the data. So I mean, what this would be saying is that in short intervals, the flares are dependent events. And then in this small interval, we see that they act as independent events. But after that,
so
after 4.5
this
days,
homogeneous, this is for combining data from multiple active regions, right?
Yes. Yep.
Why would there be a dependence across different active regions for any interval at all?
Sorry, say that again.
I mean, I understand. I mean, yeah. There is a dependence of active regions themselves in that because of the solar cycle. But over, let's say, 1 day or half a day or 6 hours or whatever, why would you find the flares in an active region that's very, spatially very far off?
Oh, so basically, when we do that counting, we're each active region, we do that count. So in my previous example for the active region 1275, I had that table, which basically was the flaring in some interval, right? Yeah. And that was basically in the homogeneous results, we produced this table for many active regions, and we basically sum up all the tables. So it's not saying that there's dependency between active regions. This is just looking at time intervals.
Oh, you're just increasing your sample size, but you're still limiting your data to individual active regions. Okay.
Did you guys, sorry, this is Charlie. Did you guys do a simple check on generate data as a completely independent of each other, running your test and see if you have these peaks once in a while? Because, there's obviously when you do those things, those peaks is you obviously have the multiple comparison problem even when you run it long enough. I just want to see how often those things will happen. And it won't surprise me that the data completely independent generated, you will still see something of this nature.
That's a very good point. Or in other words, we want to have like a p-value interval or like some kind of uncertainties of the p-values here, right? To see if they're truly significant or something like that. So you're saying you want to have synthetic data to see whether, so you want to calibrate our p-values.
Exactly, because I mean, this is like, for this, the genetic study, they would do this kind of a, not just, because you have so many p-value over time, you want to do a, what I call the genome-wise p-value, right? Because they're, the level,
type of thing.
The levels are much, much smaller because you have so many.
Or
the
lookout square effect in physics, right, is looking at that same thing, because as you look at different resolutions, different p-values, so they look at the maximum p-value of that, and then you have to figure out how to calibrate it. So that in physics, they do mathematics. It's not so different than this question. It might be worth looking at that. There's a mathematical correction that they do to the p-value. That's the maximum.
Yeah.
Right. But the first instance would be just to do a simulation to see if maybe you'll do it and you see that you don't get peaks like this, and then maybe it's nothing to worry about, but it's worth at least looking at those simulations. Might give you some ideas about how to proceed.
Right, and my hunch is that there's peaks you will see, but when you do simulation, you do need to be a bit careful, because you want to. I mean, you still want to mimicking the same behavior, except you don't want the dependence.
Yeah, you just match the marginal distribution by trial and error.
Yeah. I mean, because when you do those things, like these corrections turn out to be crazy, right? If you look at these genome-wide studies, their p-value, the requirement is 10 to the minus 6 or 10 to the minus 7 because of the adjustment. So it's not trivial, right?
You could take your real data and, well, gosh, it's not at the highest resolution, I guess, and then just randomly permute it.
Exactly.
And that would be then you'd have it seems like you'd have the relevant characteristics of the data, but then
your margin,
Oh yeah, that's a good idea. Just to permute your data, right? Yeah, that's a good point. Yeah, we should definitely check it out. And the other thing is that 4 to 6 days is close to the like the lifetime of the active region for many cases. So that's another suspicion there.
Well, I did check on that. And so here's like the histogram showing like the number of days that we actually observed the active region. So
how long do you see the face of the sun before, because the sun is spinning, right?
Yeah, relative to Earth, yes.
15 days.
15 days, so 6 shouldn't matter then. Maybe that's why you see the 15 days here, though, because the active region will go back around and you won't see it, right?
You label it as a new active region.
Yeah, when it comes back.
Yeah. And there's no way of matching them. That's also the complication of the data. Yeah, we definitely need to do more testing on that. Yeah, the multiple testing correction is another thing for homogeneous test case that we haven't really studied a lot, like Bonferroni or FDR control.
There's something called the maximum p-value, where you take the maximum, which has its own distribution, and then you can use that one to get your adjustments. But can I ask, for a given delta here in that picture, is it a single 2x2 table you're computing the p-value from?
Yeah.
I thought it is, right? Because you're getting all the information together.
Yeah. So adding up the counts instead of adjusting for multiple testing, which is something that we definitely can do.
But there really isn't any multiplicity here, because it's a single, suppose delta is 1. So you're looking at distances of 1 days. You get your 2x2 table, you do your permutation test, and that will give you the p-value. And then you're just plotting that for every delta. Or am I misunderstanding the plot?
That's correct.
the multiplicity will come in, right, if you do it for every active region separately. And then you have to combine those p-values.
Yeah.
Yeah.
But that's also under homogeneous assumption, whether there's a dependency or independency across all regions. But then in the whole heterogeneous test that Noah is saying, there's a bunch of active regions that have dependent structures, but there are also some active regions that do not have dependent structures. Yeah. But yeah, I think I like this discussion. I think this will make our homogeneous case richer in a sense that not only combining the counts, we can also combine the p-values in a principled way and check out the results.
All right, I'm gonna move on. So when we actually consider, this is just, I haven't found a really good way to actually go about showing this in some nice plots, but we can test subsets of the data where we look at just the relationship between the strong flaring as well as comparing strong flares to weak flares. So there, I mean, I haven't found any interesting plots because, I mean, they're essentially the last plot you saw, but it's just a significant p-value that's below, 0.05. I guess the most interesting would be when we consider just weak flares, which means just subsetting the data, just taking B and C flares. We see that when doing the homogeneous test, we get basically a significant p-value up until about 3 days, at which the weak flares act more as if they are independent events. So, yeah, there's still more work that needs to be done here. Like I said, there's just so many different hypotheses you can test between looking at, there's 5 different classes, and then if you look at all subsets of those, you get a lot of different tests that you can do. So moving on to the heterogeneous results. So this plot is just showing you just the distribution of the number of flares that occur within each active region. So I show this because I wanted to show you that there's a lot of sparsity in this data set, meaning there's a lot of active regions that do not produce a lot of flares. There are very few cases where you have these insane, highly active regions where you have a lot of flares. And this is actually what led us to split up the active regions into 2 different classes. Basically, we split up the data into active regions, which we considered. Sorry. Oh, you already answered. Okay. So we considered active regions with less than 10 flares to be relatively quiet active regions, and if an active region had more than 10 flares, we considered it to be a highly active region. And that just makes it easier on showing the heterogeneous results in this plot is here. So this plot is different from the previous plot. So this is given a certain class of active region, whether it's very active or very quiet. We are plotting the proportion of significant active regions in that class. So again, we see for each class, and then this blue line is actually just considering all active regions, not giving them any subclass. So this is basically a weighted average between these 2 lines. And we still see that the largest dependency is around 3 days when we see flares are the most dependent on each other. Again, we don't do any splitting of the classes here because we would just actually, these are already, especially for the low flaring or low activity, this would just further decrease the sample size of the test. So. And then So yeah, that's basically it. I mean, in summary, the solar flares are just highly dependent events. We see that in both quiet and active regions. About 3 days is when we see the largest dependency between solar flares. And this actually didn't point out to me until somebody told me at a conference, but the flare dependency is not monotonic in the time interval considered. Actually, somebody thought it was most interesting because they thought that they would be most dependent in a very, very short interval. But that's not necessarily the case. In extremely small intervals, we see that they are not, they would be independent events, which, like you said, is probably just because the sample size is, there's just mostly no flaring. But like I said, we see that peaking around 3 days. And then lastly, for weak flares, after 3 days is when weak flares, we can consider weak flares to act as independent events. So, and yeah, so that's really all I have. I'd love to take any questions or appreciate you guys having me.
Thank you, Noah. That was a very interesting talk. Any questions? Or should we wait until? No, maybe we should. If there are any questions, let's have them now, because I think the next topic is different. Oh, Gwen, yes, you have a question.
So maybe this is more of an idea, and maybe a terrible idea. I'm not sure. That's fine. So then when we it sounds like one of the goals you have is to compare or to find out if a bunch of low energy flares lead to more high energy flares. Is that right? So I'm wondering if I'm just thinking of like first year stats courses that I've taught, and a common example is that you have a farm and you want to examine some sort of fertilizer and look at the yield of that fertilizer. So like you have 2 plots of land and you apply the fertilizer to one and not the other, and then look at the yield and compare the yield. And so the fertilizer is the treatment. So in this case, could you kind of do that with these active regions and say these are the plots of land and the treatment is a bunch of low energy flares, and then kind of compare what's the yield of the high energy flares? Like, or is that, maybe that's a terrible idea? I don't know.
No, yeah, I hadn't thought about it that way. So basically just count the low energy flares within each field and say that come up with the distribution or probability of having a certain amount of high active flares given that you see this amount of flares.
Right, exactly. Yeah. So I guess you'd have different amounts of treatment for each one.
Yeah.
But I imagine the actual analysis of it might be pretty simple, but maybe it would tell you something.
Yeah, no, I really like that. Thank you.
Yeah, that's a really interesting thought. We can definitely try it out really quick.
Yeah, and it seems quite simple, like you said. It's
yeah.
It's just it's just really coming up with the distribution and just I don't know.
I'd be really curious to see what you find out if you end up doing that. So,
yeah.
Yeah, we'll send it to you for the course material if we get anything.
Okay, cool. Yeah, keep me in the loop. Thanks.
All right, Yang, do you want to take over the screen share?
Okay. Do I have any more comments or suggestions or?
The one follow up on on Gwen's suggestion is that it's difficult to focus on the weak flares because they are difficult to detect, and especially during solar, the peak of the solar cycle, you tend to see fewer B class flares because they get drowned out. You don't see them. So there could be sensitivity issues that just to just keep that in mind.
Sensitivity is in the
detection sensitivity issues.
The sensitivity in the solar minimum?
No, at solar max. So you're going to see fewer B flares during solar max.
Oh yeah, because the sample collection thing. Yeah, actually, no, you had that idea of.
Yeah, so this got brought up when I was talking to somebody. They said, so since we consider an entire solar cycle, it would be also interesting to look at some period around solar maximum and a period around solar minimum, seeing if they vary in terms of the dependency structure. So seeing, you know, like at solar maximum, you know, these are really dependent events, but, you know, potentially at solar minimum, they're in shorter intervals, maybe more independent. So
yeah, the active regions tend to be more active during solar max than solar min, but it's only a tendency. It's not always true. So
yeah,
I've got a quick comment just on a different way of looking at this is looking at inter-arrival times, right? That between flares. You assume the basic Poisson process, right? Then you would get exponentially distributed into, you know, times between flares. And that's not the case. I think that's what we found out in the different data analysis part. It doesn't then mean that they're dependent or anything. It doesn't say much about that. But maybe there's a way to study those time between flares, their distribution, to see if we can conclude something about correlation.
Actually, that's an excellent point, Bernard, because the actual observed waiting time distributions are more power law-like than exponential for flares. I wonder if you can get that from this kind of dependency. That will be interesting to see.
Mm-hmm.
Or even like just draw a histogram of the time between flares for those things you identified as not correlated and the ones you did as correlated, just to see if there's a big difference.
Yeah, that's
that'll be interesting. Yeah. Because when we just pull all of the intervals together, it was not really an exponential distribution apparently, but we were able to fit it pretty well with a mixture of exponential distributions.
Oh, are you? Okay.
That was now I remember the work that Chikai did. So we were very ambitious. We were trying to come up with a very big, large-scale simulation pipeline for solar flare events coming from the predictors. And then we had to study the marginal distributions of the flares and their intervals and stuff like that. So we were able to use the mixture of exponentials to approximate the marginal distribution of the flare intervals, but that is just for any flare. So it's putting a lot of things together. But I think what Bernard is proposing is to study the ones that you identify as dependent and independent, and separate those distributions to see if you get an exponential distribution on that.
Yeah.
I think we should check it out because it's like a byproduct for our result.
I know some work Josh did. We only looked at active regions that have at least 50 flares in them, but you showed a histogram. And for those we found 50% of those roughly actually did have exponential waiting times, and the other 50 did not.
Interesting.
Okay, so that might be a nice mixture distribution there.
Yeah.
Okay. All right. So we have I don't know 15 minutes for you. Yeah, on CStat.
Okay. I'll do it in 15 minutes. So can you see my slides?
Yeah.
I have a very wide screen. So I briefly talk about the goodness of fit in astrostatistics using the C statistics. This project actually started from many years ago. And then like a few weeks ago or a few months ago, Max Bonamenti from UAH gave a presentation. And then he followed up with me sending 3 very, very long emails asking clarifications about C statistics. And then I realized that we owe this community, especially the astronomy community, a paper on C statistics. So I quickly put together some results, and we're writing this paper right now. So I just first define the C statistics and show a few asymptotic results that we derived to justify for the 4 different algorithms that we come up with using C statistics for goodness of fit assessments in X-ray physics. And then we'll talk about a few numerical studies. They're not extensive yet, and then some real data applications. So the entire history of C statistics in astrophysics is that at the very beginning, people used the C statistics to obtain the maximum likelihood estimation for unknown parameters for heterogeneous Poisson count data and try to obtain confidence intervals. And then they still use the chi-squared statistics for the hypothesis testing problem essentially trying to test whether the model is a good fit or not. And then in the 2017 paper by Yela Castro, he began using approximate Gaussian distributions of the C statistics, but he's using one version of C statistics, which is different from the actual C statistics that people use nowadays, and to perform goodness of fit again. And then in 2022 and 2020, Max from UAH followed up with some more results and more numerical approximations, still using Gaussian approximation. So the formal definition of the problem is that we have independent Poisson observations. Ni is the Poisson count, and then Si is the Poisson rate. And then we have many bins from 1 to I. And then the SI is parameterized by a parameter theta that we need to estimate using maximum likelihood estimation. So the MLE problem is very simple. It's a Poisson model independent of each other, and we obtain MLE. And then if we consider a saturated model where each of the SI is a free parameter that's not constrained by any parametric form, then the MLE estimate for SI is just a plug in the Ni. Then we can derive the likelihood ratio statistics of getting the null model, which is the model follows this SI theta parameterization, versus the fully saturated model where the Ni is just an independent Poisson SI. And then this particular thing that we get is the plugged in version of the so-called C statistics. So essentially the C statistics is a likelihood ratio statistics. And then more generally, we define the C statistics function as a function of theta, the unknown parameter theta, in this form that's like directly mimicking this. And then we call the C mean to be the plugged in version of the C statistics after plugging in the maximum likelihood estimate. And then we call the C true to be the C statistics after plugging in the true parameter of theta. So there are a few things that we want to notice in practice is that in the previous papers that people are confusing the plugged in version of C statistics, plugging in the MLE versus the C statistics evaluated at the true value of theta. So when you misspecify these two things, it's actually quite different statistics from a statistical perspective. And then given that, what should be the principled usage of C statistics in evaluating the goodness of fit in a model? So apparently, this same C mean cannot be directly approximated by a chi-squared statistics using the Wilks theorem, because typically the number of bins that we get is pretty large. It's around 100. And then the degree of freedom for the unknown parameter is only a few. So that means the degree of freedom for this likelihood ratio statistics is around 100. So this is a very large degree of freedom. And the Wilks theorem does not really hold here. So let's see. So by the Wilks theorem, what we can show is that the plugged in version of the C statistics evaluated at the MLE.
Sorry. Quick interruption, Yang. The Wilks theorem, you said, doesn't hold when you have a large number of degrees of freedom?
When the degree of freedom goes to infinity, it doesn't really hold. When the number of counts goes to infinity, it does hold. So we'll show that when big I is very large, actually the Wilks theorem can still hold for moderate number of bins.
So if you've got 10,000 bins?
10,000 bins, no, it's not going to hold.
Okay, thanks.
So applying the Wilks theorem, we can show that the discrepancy between the plugged-in version of the C statistics versus the true C statistics is a chi-square distribution with D degree of freedom, where D is the dimensionality of the parameter theta. So this essentially tells practitioners that you cannot be using the plugged-in version and the true C statistics interchangeably. You cannot use the asymptotic normality of the true C statistics as a proxy for the asymptotic normality of the plugged-in version of the C statistics. So what we have done is that, first of all, we can reduce the problem a little bit. So the overall assumption that we assume is that if we look at the observations from all of the different beans, if you just put them all together, we have a large count. That means we have enough observation if we just put together all of the observations from all of the beans. We don't care about whether each bean has a lot of observation, and we don't care about whether you have a large bean number or not. And because of the infinite divisibility of the Poisson distribution, we can reduce the problem to a case where we have a really large number of beans, whereas for each bean, the Poisson rate is bounded from above. So this is the reduction of the problem. And after this reduction, under very mild irregularity conditions from maximum likelihood estimates, we can show that the plugged-in version of the C statistics do enjoy asymptotic normality as the number of beans goes to infinity. And also the true Poisson rate parameter for each bean is bounded from below and above. So that's the only irregularity condition that we need. And then based on this particular result, we'll have a goodness of fit test procedure based on the C statistics, because what we can do is that we can do a Z test, and then the mean and the variance here can be estimated using Bootstrap. So that's already a procedure.
Yeah, probably it's worthwhile here to, I mean, certainly in the paper, we need to make clear, because this part might be a little bit confusing to the broader, readership from industrial stat. The number one, the reason the Wilks theorem, we need to be precise. When we say it's working, not working, it's, I mean, in a way, none of them are working, right? Because it's always about, the Wilks theorem is always about approximating something. The question is whether the remaining term will be small enough for those things to be useful.
Yeah.
So what happened here, Renee, is that when you have the number of beans goes up, or comparable to the sample size, you basically have the model parameter. If you don't have any constraints, because you have a number of model parameters, it goes up as well. And then that's where everything fails, right? The whole classical statistic is assuming the number of parameters are fixed, and the sample size go to infinity, right? So that's where things works. But once you have the number of bins, because consider every bin has its own parameter. When you don't constrain them through these cetas, then you have a number of parameters goes up as the number of the bins it goes up. So that's where you enter the large P small n framework. Now the P itself, P means scalar the parameters. So this is actually, and also, we talked this a little bit before. I think we need to change this n. This n is going to confuse people.
I know I don't like that notation, but I didn't have time to change it. Sample
size here, at the bin size. Maybe we use P or something. We need to indicate that is the number of parameter in a way. But the other point I want to make here is that we probably need to explain a little bit of this infinite divisibility, because I don't think that's a term people understand in general, even in statistics. Not too many people understand that term. But most important is to show why have this a property and have this boundness that make the kind of large P small n problem controllable, right? It's always about the idea of having the sample size go to infinity and the number of parameters are fixed. Basically saying the number of unknowns you need to estimate it will be far less than the information you can accumulate. Right, so that's what happened. So here, we need to show why this still works, because there's, as long as there's enough accumulation of the information per parameter, and that is where those things become at least asymptotically kind of works. The third point I want to mention is that although using the normal approximation is always the convenient ones. But at the end of the day, it does not really matter whether it's normal or not, right? As long as there is some way, there's a pivotal quantity, there's some reference distribution does not depend on the unknowns anymore. We can can do these tests. The reason I mentioned this is it won't be hard to imagine that there might be problems where you end up having like a mixture normal or something, depends how the problem is setting up. You can still do these tests as long as there's a reference distribution is known. Although I think that you're going to suit this to simulation, right? Because these approximation may work, but how well they work, that will be a theoretical question as well. Like, what's the order of that remaining term here?
Yeah, I think we can give some results about the remainder terms, because one of the remainder terms is really the chi-squared distribution with d equal degrees of freedom divided by the variance of the Cstat. So if if theta is of higher dimension as compared to the number of beans, then there's also that correction term. So we can definitely we can include more details in the paper about this residual term. And
this also reminds me that this is we talking about this modern challenges. This problem actually all the stuff you're doing now, we should emphasize this as getting to the more modern asymptotics. These are not the classical asymptotics, exactly because the number of things itself, because this will actually raise the interest from the theoreticians, because otherwise they just think you're just doing a classical test statistic approximation. It's not. This is actually a more complicated version of that.
Yeah, sure. Okay, great. And then so in a particular setting where we can parameterize the SI as a log linear model, in other words, if you can write the logarithm of SI as a X, some design matrix, times some unknown parameter theta. This is actually a quite a general setting in astronomy, because we can find a few distributions, for example, the Power law and the exponential rate to be following this kind of result. So if this follows the log linear model, we can actually derive the conditional expectation, the conditional variance of the C statistics, plug in the MLE when conditioning on the maximum likelihood estimate. And this gives us a more precise characterization of the moments for the C statistics. And again, using this, we can derive another procedure for goodness of fit assessment. Again, using asymptotic normality of this, but using a different formula for the expectation and variance. So here we have closed form solutions for the expectation and variance, so that we don't really need to do any bootstrap. You can imagine the computational cost for this is like trivial. So this is another procedure that we get. So as a summary of the different algorithms for goodness of fit assessment that we'll be comparing across in this paper, the first one is the chi-square statistics. So essentially we just apply the Wilks theorem blindly and then try to see how the chi-squared distribution with n minus d degrees of freedom is leading us. And then the second one is based on asymptotic normality. And again, we still need bootstrap to calculate the mean and variance for this asymptotic normal distribution. And the third one is based on this high order expansion under the log linear model framework. So we can still calculate the p-values. And then the last one is just a simple parametric bootstrap. Straightforward, computationally, it takes a little bit of time because we have many beans. So here I do one particular case study. So this is a one shot of the simulation. We have 100 beans, theta 1 equal to 2, theta 2 equal to 1. The SI follows this model. It's a multiplier of an exponential. And then we perform the test a couple of times. We just run this a couple of times or 5 times. And then the chi-square test sometimes give us a significant result, which is wrong because we're fitting this model and the count is actually pretty large. We should not be claiming that this is lack of fit. But chi-square test is rejecting 2 out of the 5 times. But then for the bootstrap test and the test based on the C-mean, none of them is rejecting. So this is just some promising results. And after that, we designed a bunch of models for systematic comparisons of the 4 different algorithms to really figure out what is the type 1 and type 2 error rates of the test procedures. So model 1 and model A and model B are designed to say, well, if the model should be a good fit, then what is the type 1 error? And then for model C, we essentially sample from a free parameter, free SI model. This is essentially combining the gamma with the Poisson again negative binomial distribution. So if the data generating model is really not following the null distribution, can we reject it? So this is gonna give us the power assessment. And then for the model A and B, we consider the varying rate and constant rate Poisson model. For the varying rate, we consider Pareto and exponential rates. So those are realistic settings that we come up with. And then in this table, it's not extensive yet, and I don't want to say too much about this result, but again, it's just showing some promising results of using the, all of the ones ending with S means we're in the small count setting, ending with L is the large count setting. So essentially in the large count setting, all of the algorithms perform very, very similar to each other, which is just a proof of concept. And then for the small count settings, we do discover that the syntactic normality-based test, bootstrap-based test, and high order expansion-based test are offering us very competitive results. In many cases, better results as compared to the chi-squared test. And then when we look at type 2 error, especially in the sparse count settings, algorithm 3, which is the one based on higher order expansions, is the one that give us the best numerical result. Or in other words, in terms of detecting the deviance from the model, algorithm 3, which is the high order expansions, has the highest power. So that's the findings so far. Again, we do need to carry out a lot more simulation studies to give us a fuller picture and give recommendations about when to use each algorithm in practice. But overall, algorithm 3, the high order expansion one, is giving us the best power and is computationally the least expensive. So there is some usage of that in here. And then for real data, we applied some data, which I haven't really gone through the detailed description of this data yet, so I cannot say too much about it. But the key message is that actually the chi-square distribution approximation do screw up in the real data, whereas all of the other algorithms do not. Like none of the other algorithms screw up in this real application. So that's pretty much the results I have so far. It's not complete yet, but we're showing some promising results.
Thanks, Yang. That is fascinating.
Yeah, you said that the theta parameters, they increase the sample size, but I think on your very first slide and then the example you used, theta is actually staying constant, right? There's as you get more data.
In the real data example?
Yeah, or even on your first slide where you define the SIs, right? The interval to bins, they depended on the theta parameter. That's really the only unknown parameter, but that it doesn't change dimension, right? As you get more data.
Yeah, the theta doesn't really change dimension. The SI theta changes, yes. In an indirect way, yes.
So what's the problem with Wilks' theorem? I thought the parameters then would stay the same as you get more and more data.
Oh yeah, if you're doing the Wilks theorem, comparing the theta versus the theta being a free parameter versus theta being fixed, then the Wilks theorem will apply. But then in our case, the C statistics is defined in a way that the null hypothesis is that it follows SI theta, and the alternative is the fully saturated model where each of the SI is a free parameter. So you have
that's like a deviance
degrees of freedom as the number of SIs that you have.
Yeah. Oh, I see.
So you do not. Yeah.
It's like in logistic regression models, right? In many of just binary data, you can use the deviance as a goodness of fit.
Right.
I see.
Right. Because the comparison, because here is trying to compare what it's trying to do the goodness of fit. So the model you have is actually fully saturated. So as many parameters as number of bins in the in the free case. So that's right. There's lastly, the real example, you're saying the chi-square screwed up. Which chi-square are you referring to? Is this the one they use the so-called exact answer because they forgot to take into the theta hat?
No, the chi-squared is chi-squared in my notation, little n minus d. That means p minus d. So
they basically screwed up there because they used the wrong reference distribution. If they change the degree freedom, if you change the degree freedom, that should be still okay. It's okay.
No, there's no way of remedy because that is the degree of freedom. It just don't have enough counts per bin. If you have enough counts per bin, they're not going to screw up.
Okay. That's
like 1 count per bin or 0 count per bin.
Yeah. That's the other problem when you have so many bins. Now, but there's a real problem here. But the real problem we're not addressing here is that the number of bins here, is it true that the number of bins that typically chosen is data dependent itself?
No, it's instrument dependent mostly.
Instrument dependent. Okay, so that's actually, so you're saying
unless you're wait, I take that back.
Yeah,
unless you're doing temporal analysis, in which case Bob's your uncle. Anything goes.
What'd you say?
And if you're doing a light curve analysis, I mean the spectra, the sizes of the number of bins is limited by the instrument. But if you're doing timing analysis, then it can be anything.
Then the question for us is that all the asymptotics you have actually assume the bins are data independent.
Yes.
If you have a data dependent bins, that's a hell of more complicated.
Yeah, because you're conditioning on that random variable.
Right. So that's actually, it's interesting that somewhere the thing can still bridge down because people do all the other. Is that possible?
Yeah, people bin the data, right?
They do, right?
Yeah, they bin. So you have, fixed instrumental binning, but then you sort of group the data to improve your number of counts per new bin. And that's, it may be that at that point you lose the independence also because you have the RMF component in the analysis. That's interesting. But I had another question, Yang.
No, and that's sorry. I just wanted to add to that because there's a bit of a cottage industry with the XSpec sort of, CStat stuff where there's stuff about how bad it is if you have zeros like in the back. Well, it's a bit more for the WStat stuff, but if you have zeros in the background, and then there's like you should never rebin stuff, but you should make sure that each bin has at least 1 count in. So there's a bit of a cottage industry and all this stuff, which is very, very related to what you were just talking about. But sorry, Annette.
Yeah, that's a very good point. Yeah, we cannot have that more than 1 count per bin thing as a pre-selection because otherwise our algorithm is completely screwed up.
Yeah, that's wrong, right? But so my question was about your algorithms versus Castra approximation to goodness of fit. Have you done any comparison between the two?
I haven't done much comparison of that, but that's easy to do because he is essentially doing the polynomial.
Yeah. So you can.
We can definitely try out like a few cases in the simulations to do a fair comparison. Yeah, and the Max also has another polynomial approximation that's very similar to.
Exactly, that's what we were discussing with.
Yeah, he even come up with his own table for lookup for significance. Like he generated his own like Gaussian tail table.
That's right. Yeah. But so all this comparison will be interesting because you have one algorithm, you have statistical base for the calculations, and then you have this ad hoc solutions which were put by people over the years. So it will be interesting to see. Yeah. Thanks. It's very nice. Yeah.
Yeah, we can work on that during the summer. Yeah.
So I have a question still regarding zeros. Since you have the n log n term. So there's sort of a breakdown of the Stirling approximation as you go down to 1 or 0 in the usual formulation of the C statistics. So is it valid? I mean, it's not what you would get with an exact Poisson likelihood.
Yeah, I know your point. So the Stirling approximation only is only useful when you try to approximate the C statistics with the Poisson likelihood. So under the Stirling approximation, C statistics actually approximates the Poisson likelihood pretty well. But then for the entire framework that I introduced, we do not rely on Stirling's approximation in any single bit. So that means we do not care whether you have 0 count or count of 1 or not. If you have a lot of zeros, that's completely fine because we're working on the Poisson likelihood.
Okay, well, in the spectral fitting programs like XBEC, they're using the Stirling approximation. So that's why I'm wondering what happens when you have 1 or 0 counts per bin. I've heard arguments that, you need the bin to have at least 1 count. And you're saying that that's not a good thing to do.
No, that's not a good thing to do. If you're using the minimum minimizer of the C statistics as your MLE, you're done. You don't need any Stirling approximation. The Stirling approximation comes in when you're trying to say, well, I still want to work with my, a short story, because we have a section in the papers addressing the Stirling's approximation, but the short story is that Stirling's approximation is not really useful here from an analysis perspective for both obtaining the maximum likelihood estimate of theta and also the goodness of fit assessment. For none of this, Stirling's approximation is useful.
Just to clarify, I mean, I think when you're saying Stirling approximation is not useful, you're saying that you don't need to make that explicit connection between C-stat and the Poisson likelihood.
You could using the Stirling's approximation, but
if you don't want to, then you don't need to.
Yeah, you don't need the Stirling's approximation. Everything here is exact. So we're trying to find the exact solution. No approximations. Ni can be 0, can be 1, can be 2, or can be 100. That's the beauty of likelihood-based approach.
All right. Well, any further comments, questions? If not, thank you, Yang. Thank you, Noah. So this has been a very interesting session. And our next session is on July 14th, I believe. So it should be hopefully see you all there.
See many of you next week in Pennsylvania.